Let us switch over to problem number 39. This problem is based on terrestrial telescope. In fact, we all know the major difference between an astronomical telescope and a terrestrial telescope. In the case of terrestrial telescope, we will be having, in addition to objective and eyepiece, there is one more lens, a third lens, which is to be called as an erecting lens. The importance of this erecting lens is, it simply makes the image formed erect by nature. In addition to this, one should understand that erecting lens will never magnify the image. That in the sense you can understand magnifying power of erecting lens is to be taken as 1. So, this is the additional feature of a terrestrial telescope when we compare that one with an astronomical telescope as such. So, this problem is simply based on the comparison of astronomical and terrestrial telescope in terms of their lengths. So, let me read out the question first. A terrestrial telescope is made by introducing an erecting lens of a focal length f between the objective and eyepiece of an astronomical telescope. Then its length increases by an amount equal to what? The concept you should understand in this case is, where do we keep the erecting lens in between the objective and eyepiece of an astronomical telescope to convert that one into a terrestrial telescope. What is the concept here? You try to recollect. There will be one lens like this. This, of course, we call this one as an objective. Focal length is FO. The image is going to be formed here at its focus. Here we keep the erecting lens in the terrestrial telescope. This is what we call it as erecting lens. If its focal length is f, at what distance we keep this erecting lens? You all know pretty well, the erecting lens is to be placed at a distance 2f from the real image formed by the objective. So, what we should understand in this case is, this image formed by the objective should now be at its center of curvature. That is the concept. Then automatically we will be finding its image again be formed by this lens. At what distance the image will be formed again? Again at the same distance 2f only. So, if you take this image as AB, that is real image formed by the objective, its image again is formed as A dash B dash here with the same size. Every dimension of the image and object are equal, but this is reversed image of this or inverted image of this inverted image, which is now becoming an erected image there. That is the concept. So, if you take the third lens over here, that is the eyepiece, what we people are talking about, then the final image will now be formed at infinity. That is actually the case. Like we will be getting parallel rays and all, and of course final image is going to be formed at infinity. This is the rough sketch of that terrestrial telescope. If you take the final image to be formed at infinity, this point must be its focus. So, you definitely can understand this is focal length of eyepiece. This distance is focal length of objective. This total distance is 4 times the focal length of the erecting lens. Then when I consider the length part of this terrestrial telescope is equal to FO plus FE plus 4F. This is for which telescope? Terrestrial telescope. Terrestrial telescope. Suppose if I write for astronomical telescope, for an astronomical telescope, what can we write? the same length formula FO plus FE only, because no erecting lens that is introduced in this. So if you take this first one and second one, compare them, what is the additional length you are getting? Additional length is nothing other than 4F. So that is what he is asking you. When you are introducing an erecting lens in between the objective and eyepiece of an astronomical telescope, and if the focal length of the erecting lens is given as F, then the length increases by an amount of what? By what amount over here? 4F. Therefore, the correct option what has been given, you look at. First option is given F, second one 2F, third one 3F, and fourth option 4F. So what is the correct option over here now to be taken? You can write that one directly. The answer is D. That means 4F will now be the increment or increasement as far as the length that is concerned. So then its length increases by an amount equal to, what is that option? 4F. That is the concept of problem number 39 what we have. A simple comparison between astronomical telescope and terrestrial telescope. That is the concept. Check the next number, that is problem number 40. An astronomical telescope has an angular magnification of 5 for distant objects. The separation between the objective and eyepiece is 36 centimeter and the final image is formed at infinity. Observe this wording carefully. Final image is formed at infinity. If you take that one separately, you can understand that the telescope is at normal adjustment. Whenever a telescope is at normal adjustment, it is understood the final image is going to be formed at a far point. That far point is nothing other than infinity for human eye. That is the point we have to understand. Now it is formed at infinity. The focal lengths of the objective and the eyepiece respectively are. The options are given this way. First one 20 centimeter and 2 centimeter. Second option given 30 centimeter and 3 centimeter. Third option is given 40 centimeter and 4 centimeter. And fourth option is given 30 centimeter and 6 centimeter. In reality, this type of a problem you need not work out. By looking to the options also you can decide your answer. For example, see the first option 20 centimeter and 2 centimeter. When the image is formed at infinity, then what is the magnification formula? Magnification is going to be FO by FE. How much is given in the problem? It's given 5. So here if you take the first option and calculate magnification, 20 by 2 you will get 10. But in the problem it is given 5, therefore first option is not correct. 30 by 3, the second option also is giving you 10, so second option is not correct. 40 by 4, that is also given 10, therefore third option also is not correct. Then what is the only option left means the fourth option. 30 centimeter is focal length of objective, 6 centimeter is the focal length of eyepiece, 30 by 6 will now be 5. And what about the length? Length is FO plus FE, that now must be 30 plus 6, that must be 36 centimeter. So directly you can identify the answer as the fourth one. But let me write two formulae here. When the image is formed at far point, image at far point, that is a concept what has been given there. Then magnifying power of that instrument is FO by FE. And of course we know the length part of it, L is equal to FO plus FE. Magnification is given 5 and length is given 36 centimeter. Come on, just solve these two. You will be getting FO as 30 centimeter and FE as simply 6 centimeter. So directly even without doing the problem also you can check it. 30 by 6 is 5, 30 plus 6 is 36. According to the given options you can decide your answer there itself. This is one of the concepts what we have to understand from this model. So the correct answer for this one is also the same, that is D, the fourth option is the correct option for it. But only thing you need to understand is whenever image is formed at far point, magnification has this formula FO by FE and length has got the formula FO plus FE. That is the point we have to understand. So this is problem number 40 what we have here. Another problem based on telescope we have taken in the case of 41st problem. Problem 41 says a telescope is formed from an objective lens of focal length 60 centimeter and an eyepiece of focal length 5 centimeter. It is focused on a distant object in such a way that parallel rays emerge out of the eyepiece. Once again try to understand this wording carefully. Parallel rays are emerging out of the eyepiece. What is the meaning of it? When rays are coming out parallel, where will these parallel rays meet? According to theory, we say that parallel rays will meet at infinity. That means the final image is going to be formed at infinity. That means once again one can say that this telescope is at normal adjustment. That is the point we have to understand. And another thing what he is giving, let us continue. It is focused on a distant object in such a way that parallel rays emerge out of the eyepiece. Fine. If the object subtends an angle 2 degrees at the objective, then the angular width of the image will be how much? The options are given this way: 50 degrees. The second option is 10 degrees. Third option is 24 degrees and fourth option is given as 1 degree. One should understand a simple point here. Whenever we consider a telescope or a microscope, in most of the cases we people used to calculate angular magnification only. Reason of course is being known, very clear to us. What is the angle subtended by the object at the objective? What is the angle subtended by the image at the eyepiece? When you take these two angles, the angular magnification can be written as angle subtended by the image divided by angle subtended by the object. That angular magnification and linear magnification, whatever we used to consider, they numerically are going to be one and the same. So in this particular case, what are the values he has given? Let us first of all identify. Focal length of objective is given 60 centimeter and focal length of eyepiece is given 5 centimeter. That's what has been given. This is the pair of values what he has mentioned. Fine. Then what is the other one he has given? Angle subtended by the object. Object always with respect to the objective only we consider. Therefore, angle subtended by the object at the objective glass, that value is given 2 degrees. And what is his question there? What is angular width of the image? Angular width of the image is nothing other than angle subtended by the image at the eye, or you can even call it at the eyepiece. That value is how much? But if you just look at, there is a direct relation between this linear magnification and angular magnification. They are numerically one and the same. Okay, so how to write that? Usually magnification, when the final image is formed at infinity, in the case of a telescope, we write that one as FO by FE. That itself, we write it like this: angle subtended by the object, if I take alpha, at the eye, that is that image, if it is making an angle beta at the eye, then we write generally tan beta by tan alpha. This is tan of angle subtended by the image at the eye. this is a tangent of angle subtended by the object at the objective. Fine. But when alpha and beta values are numerically very small, then we people used to write the same like this as beta by alpha. All of you can understand limit theta tends to 0. Tan theta by theta is 1. That in physics we people used to take up like this: when theta is very small, tan theta can be written as theta, or tan theta and theta are nearly equal, like we people used to consider. Now even in this case also, tan beta now can be written beta, tan alpha can be written alpha. Then we can now equate these two values directly. FO by FE is equal to beta by alpha. What are the values he has given? You just look at FO 60, FE 5 is equal to beta to be calculated, and alpha is given 2 degrees. So what will you get out of this? Beta now becomes 24 degrees as such. So what is angular width of the image? That is the question what is asked. That in other words, we can say what is the angle that is subtended by the image at the eye or at the eyepiece, because our eye is very close to the eyepiece. Whether you calculate the value at the eye or at the eyepiece, they are nearby one and the same. They are almost equal. We used to take them equal only. That is the concept. So we can write 24 degrees. So the correct option for this particular problem is going to be C for us. He has given 50 degrees, 10 degrees, 24 degrees and 1 degree. So third option is exactly coinciding with the calculated value of 24 degrees whatever we have got. So angular width or angle subtended by the image at the eye or eyepiece, both are numerically one and the same. Observe that particular point carefully. Remember this formula. By equating these two, we directly can get whatever the value we just require. So this is problem number 41 what we have here. Look at the next number, that is problem 42. A magnifying glass. First and foremost, you should understand, magnifying glass is nothing other than a single convex lens. It is nothing other than a simple microscope for us. So magnifying glass and simple microscope both are one and the same. A magnifying glass is made of a combination of convergent lens of focal power plus 20 diopter and a divergent lens of focal power minus 4 diopter. So he is just giving us, instead of one convex lens directly to be used there, he is taking a combination of two lenses like this. Of this, the power is plus 20 diopter. Of the second one, the power is minus 4 diopter. So you can understand P1 refers to convex lens because of positive value. P2 refers to concave lens because of its negative value. Fine. What he is asking? If the least distance of distinct vision is 25 centimeter, least distance of distinct vision is also called near point of the eye. Usually for a perfect eye, the near point is 25 centimeter and far point is infinity. So the boundaries or the range for human eye, a perfect human eye, is from 25 centimeter to infinity. Any object whatever is there in between these two limits, like the eye would be in a position to see that one clearly. That is the idea. Now what is this question? If least distance of distinct vision is 25 centimeter, the magnifying power is how much? Why is he giving least distance value in particular in this problem? When he is giving least distance of distinct vision as 25 centimeter, it is understood that the image is formed at near point. Suppose if it is not mentioned like, then he would have given us directly when the image is formed at far point or at infinity like. But in this problem, he is giving us least distance. That means the image final is formed at near point of the eye. So what we can understand in this case is what is effective focal power first of all. No doubt when lenses are in contact with each other, P1 plus P2 will be the effective power. So this now to be taken plus 20 minus 4, that is plus 16 diopter. Fine. What would be the effective focal length from this value? 1 by focal power effective. That is what we will be writing as effective focal length. This now should be written as 100 by 16 what? Centimeter. 1 by 16 if I write, I will be getting in meter. Now 100 by 16 is in centimeter, that I can write simply 25 by 4 centimeter. I leave it like this. Later on I will calculate the remaining. So effective focal length we have got of this combination. Then when the image is at near point, that only has given you as least distance of distinct vision, that is at D. Then what would be the magnification? 1 plus D by F, that F is now to be called effective focal length. And we know this value of D is given 25. So 25 by 25 by 4. So total value will now be how much? Simply 5. So the magnification or magnifying power of this simple microscope, that now must be 5. So seeing the options, first option it is 3, second option it is given 4, third option is given 5, and fourth option is given 7. So this is exactly the third option what has been given over there. Then we can write directly the answer for this particular question as C. So this is the method we people have to adopt, and we have in fact two formulae for magnifying power of this instrument called simple microscope. One, when the image is formed at near point, it is 1 plus D by F. When the image is formed at far point, that is at infinity, then we will be getting simply D by F. That is the formula. The difference between this magnification and that magnification at infinity is simply 1. Only 1 will be the difference between these two values. So in this problem 42, the correct magnifying power is 5, which is the third option here. Problem 43 next. The magnifying power of a compound microscope is 20, and the distance between its two lenses is 30 centimeter when the final image is at the near point of the eye. If the focal length of the eyepiece is 6.25 centimeter, then the focal length of its objective is how much? One thing you should understand, first of all, focal length of objective when comparing to that of eyepiece in the case of a compound microscope must be less than the focal length of the eyepiece. Focal length of objective is less comparing to the focal length of the eyepiece. But all the 4 options are given less values only, less than 6.25. First option 2.5 centimeter, second option 3.5 centimeter, third option 4.5 centimeter, and fourth option is 5 centimeter. So you cannot guess any answer out of them because all the 4 are one and the same, like almost less than 6.25 only. So we just have to work out. Magnifying power of a compound microscope is 20 and the distance between the two lenses is 30 when the final image is at the near point of the eye. So we can understand directly this way, final image at D, that of course we call it as near point. Then what is magnification formula first of all? We all know that one very well, VO by UO into 1 plus D by FE. That is one way of writing the formula. The other method of writing the same formula is VO by FO minus 1 into 1 plus D by FE. This is also the same VO by UO can be written as VO by FO minus 1 into 1 plus D by FE. That is the other version of the same formula, that is for magnifying power of compound microscope. Fine. What next he has given? Length part of it he has given. Length L is equal to VO plus UE. And all of you should understand what is this VO here. It is image distance with respect to the objective. And this one is object distance with respect to the eyepiece. Which one will be an objective for the eyepiece? The image formed by the objective behaves as an object for the eyepiece. So rough sketch if I make it here, if I take this one is the first lens, that is objective, FO the focal length. Now we people are getting the object is placed somewhere here, the image is formed somewhere here. The second lens will be like this now. This is what we call it as eyepiece. Its focal length is FE. And when you take this one, the image finally is formed somewhere here. This actually is 25 centimeter, right? That is the image distance from the eyepiece. What is this 25 now to be called? Near point distance or least distance of distinct vision. Now if you look at carefully, AB is the object for the objective. A dash B dash is the image formed by the objective. Fine. That image becomes an object for the eyepiece now. When this is an object for this eyepiece, this becomes the image formed by the eyepiece. So this now can be taken A double dash and B double dash. This is the way. This is the final image which is formed at 25 centimeter according to him. Now you can understand well, this distance is called VO, image distance from the objective, and this distance is called UE, this is object distance from the eyepiece. This distance totally is given as the length over here in this problem, and its value is given as 30 centimeter. And what is this question? Focal length of eyepiece also he has given you. What is the focal length of eyepiece that is given? It is 6.25 centimeter. 6.25 centimeter. What is the focal length of this objective? That is the question he is asking. In fact, that is what is to be calculated now. For that, I start my calculation right from the eyepiece onwards. We know very well, for the eyepiece, observe this point carefully, for the eyepiece, 1 by UE plus 1 by VE is equal to 1 by FE, the formula general. Because there is a convex lens, we can understand that one very well. Now what I can write in this case is 1 by UE is equal to 1 by FE minus 1 by VE. But if you look at carefully, this is 1 by 6.25. This is 1 by 25 centimeter. I should write with a negative sign. Then automatically you will be getting this one 25 LCM and 5 in the numerator. This minus of minus becomes plus. So what will now be the value of UE? It's simply 5 centimeter. When this distance is 5 centimeter, what will be the remaining distance then out of 30? The remaining distance must be 25 centimeter for us. So what can we write now? Therefore, VO is equal to 30 minus UE, which now becomes 25 centimeter. So in this formula, VO is known to us as 25. Magnification, of course, he is just giving us as 20. D is 25 centimeter we know, FE is 6.25 centimeter we know. The only one value which is not known to us is FO. The one and only one value what is not known to us in this formula, that is focal length of objective only. That only he is asking you to calculate. So let us calculate the same thing here. The same calculation I just write. Magnification, that's 20, is equal to VO by FO minus 1. VO of course we have got 25 by FO minus 1 into 1 plus D by FE. D being 25, FE being 6.25. 25 by 6.25 is going to be 4. 4 plus 1 now will be 5. So directly I write that one over here. So what can we write now? 25 by FO. If I write 20 by 5, that now becomes 4. 4 plus 1, that now becomes 5. So what you can understand from this? The focal length of objective now becomes 5 centimeter for us. So what is the value of focal length of objective is the question. So what I have done in this particular case, you people can understand, considering the eyepiece, I have calculated the object distance from the eyepiece. And I know VO plus UE is 30. Therefore, substituting that value here, I have calculated the image distance from the objective as 25 centimeter. In terms of these values, magnification has got a formula this way. VO is 25 centimeter, D is already known to us 25 centimeter, FE is given 6.25 centimeter, and magnifying power is given already in the problem as 20. Only value which is not known to us is FO. Find out that value, you will be getting 5 centimeter for that. And 5 centimeter according to the given options, it is the fourth option. Therefore, option correct answer for this one is D as far as this problem number 43 that is concerned. So the calculation part you just go through, and it's a very simple one, only formula oriented. If you are familiar with the equation thoroughly, you definitely can do that one, it's not a big task. So this is the correct answer, that is 5 centimeter, which is the fourth option given in the problem as such. From the next problem, that is 44th number onwards, few problems we have taken based on eyepieces. In fact, we are all aware of two different eyepieces in fact. One of course is Ramsden's eyepiece, one is Huygens eyepiece. By using these two eyepieces, we can minimize the aberrations which are possible or which are going to be observed in the case of optical instruments. Mainly our concentration will be on two aberrations. One is chromatic aberration due to the coloring of the incident light, and second one is spherical aberration. So these two aberrations, to minimize them, we have constructed two different eyepieces. One is by Ramsden, that's called Ramsden's eyepiece. One is by Huygens, that is Huygens eyepiece, what we call it. But out of these two, Huygens eyepiece when we consider, it minimizes both the aberrations to the extent possible. Now this problem 44 is directly based on Ramsden's eyepiece. In the case of Ramsden's eyepiece, L is the length of the effective eyepiece. Length of the effective eyepiece means nothing other than the distance of separation between the two lenses used in that eyepiece. In fact, we all are aware of this point as well. Two plano-convex lenses having same focal length are separated by a certain distance equal to 2f by 3 in the case of Ramsden's eyepiece. So what is this value of L he is giving us now? It is simply 2f by 3. That is the effective length of the eyepiece. Length is nothing other than distance of separation between the lenses. Now come to the next one. FF is the focal length of the field lens, and FE is effective focal length of the eyepiece. You can understand now FF is focal length of field lens, but you know pretty well in the case of Ramsden's eyepiece, field lens and eye lens both will have the same focal length, F each. So automatically we can write focal length of field lens becomes F only now. But what next he is asking? FE is effective focal length of the eyepiece. What is going to be effective focal length? Effective focal length. Effective focal length of Ramsden's eyepiece is 3F by 4. All these formulae you people should be thorough with. What is the length between the lenses in the case of Ramsden's eyepiece? That's 2F by 3. What is the focal length of field lens? F. What is focal length of eye lens? That also is F. What is the ratio? 1:1. What is the effective focal length of this Ramsden's eyepiece? That is 3F by 4. What is effective focal length of Hygen's eyepiece means 3F by 2. There is a difference between these two formulae again. Now what is this question? Then L is to FF is to FE. That is the ratio he is asking. The moment you can recollect these three formulae to mind, that is not a problem to calculate the ratio. Is 2F by 3 is to F is to 3F by 4. That of course you can write 2 by 3 is to 1 is to 3 by 4. So suppose if we take 12 like this, now becomes 8 is to 12 is to 9. So where is that particular ratio given? You just check it. The very first option, if you look at 8 is to 9 is to 12. Second option given is 9 is to 8 is to 12. Third option is given 8 is to 12 is to 9. And fourth option is 9 is to 12 is to 8. So we people have got 8 is to 12 is to 9, which now is in coincidence with the third option given in this problem number 44. So we can directly take this answer as C for this problem 44 as such. So length is 2F by 3. Focal length of field lens is F. Eye lens also is F. Effective focal length will be 3F by 4. These are the main formulae one should have in memory as far as Ramsden's eyepiece that is concerned. And most of you people must be aware of Ramsden's eyepiece is called positive eyepiece. And crosswires you can arrange them. You can use that one for measurements, particularly in physical microscopes and telescopes. We people used to find Ramsden's eyepiece and the use of that. So these aspects, in addition to these points, one should remember as far as Ramsden's eyepiece that is concerned. So this is problem number 44 what we have.